Hi everyone. Before we start, I would like to thank you all for being here with me, even though I cannot make it to showing up in Canada in person due to my visa issue. And I wish I could be here in person to hear more ideas and get more insight from you all, and wish we could have a good time. Alrighty. My name is Chenhan Zhang, and I'm a PhD student at the University of Arkansas, and I'm pleased to present my work, Shape Sensing of Continuum Manipulator using Sliding Resistive Flex Sensors, and my collaborators are Shaopeng Jiang from EPFL, Heyun Wang from Johns Hopkins University Mechanical Engineering Department, and also the rest of the collaborators are Dr. Joshua Liu, Dr. Amit Jain, and Dr. Mehran Armand. And this research is part of our ongoing effort to develop affordable, accurate, and real-time shape sensing solutions for continuum robotic manipulators in orthopedic minimally invasive surgery. So to start with, Continuum Dexterous Manipulator, which we also call CDMs, are flexible cable-driven robot in effector that can bend and navigate through the constrained and narrow spaces. The snake-like structure and the smooth, compliant motion make them ideal guiding tools for minimally invasive orthopedic procedures, such as debridement in the THA surgery, where precision and the accessibilities are essential. As we can see from the second picture, in the traditional way, rigid tools lacking reachability and were too bulky to reach all of the target lesions, surgeons often have to remove extra healthy tissues to ensure the success of the procedure. With assist from the CDMs, we can clearly improve the accuracy and reachability of our surgical tools to make it a more elegant way. However, one of the key challenge for continuum manipulators during the surgery is accurate shape sensing, which means we wanted to know the exact shape of our continuum robot to avoid unexpected collision with healthy tissue during the operations. And the object of this work is to develop the feasible and affordable shape sensing system for continuum manipulators using sliding resistive flex sensors, which we call RFS, combined with a residual network. Specifically, our goals are first to design a sliding sensing mechanism that allows a small number of flex sensors to measure the local curvature along the CDM's body. And second, to establish the stable and repeatable data acquisition platform for our model training. And third is to train a data-driven ResNet model that can accurately reconstruct the CDM shape in 2D space. To achieve our goal, we research existing masses, and each of them comes with some limits to our application scenario. So start with the traditional model-based approaches. It's highly reliant on the kinematics and dynamic models, which are computationally expensive, and they are sensitive to the external uncertainties, which means due to the compliant nature of our continuum robot, the shape are easily defined and affected by the external forces or the environment. And second, in our robotic prediction space, the viral-based methods, which also called image-guided surgeries, are pretty popular concepts. They're more likely to use the optical cameras, MRI devices, or C-arm devices to provide high accuracy image to guide the surgery and our operations. But they are not very impractical due to the line of sight issues of optical camera, and C-arms will have radiation concerns due to the X-ray, and the MRI devices are sensitive to the metal tools during the uh, optical during to the orthopedic surgery. So the third way is the sensor-based methods, such as electromagnetic tracking system. We call it EM trackers. They're pretty much small and elegant. They're easy to embed and integrate it to the small-scale robot surgical tools like our CDMs. However, they're also sensitive to metal tools during the surgery, so they're not actually working. And also, we are known the optical fibers, which we call FPG sensors, is very popular in this continuum robot shape sensing field. However, due to it's very costly, it's very expensive, and they are fragile and sensitive to the temperature changing, the high frequency vibration during the bone surgeries drilling a million, and they're also sensitive to the moisture changes. So, therefore, we are proposing low-cost, robust, and precise sensing solutions that can provide real-time feedback for our CDM system. So I'm gonna introduce our proposed system and approaches. Our approach is integrated with start with the hardware innovations and also the data-driven model. So as we can see from the picture on the bottom, we embedded the two well-established resistive sensor, flex sensor into the CDM body, and the whole system just integrated with the depth camera on the above, just to help us to detect the position of our each joint. And also we have two RFS sensors embedded in the CDM channels. We have two encoders to get the position of our uh, RFS sensors to know like which joints we are actually measuring. And also we have like two linear motors to drive our CDM's motions. And uh, the sensors are this design just significantly reduce the sensor count and the complexity of the whole system, which maintain the coverage of the entire manipulators. And the sensors are just embedding and sliding along the CDM, allowing them to scan the local curvature and help us to get the joints just by two strips. And secondly, we're going to introduce our experimental platform for data acquisition and collections. As we can see from the picture on the top right, uh, for the ground truth acquisition, the camera-based vision system just detect the color markers place and align the CDM body to record the joint position. And simultaneously, the encoders and RFS signals just recorded from the hardware system uh, can help us to get the motion of the we recorded those motions and the signals. And then we synchronize those data to form our data sets for sensor values with sensor values and ground truth shape under the various CDM configurations, which are later used for neural network training. And then we're going to move to our more introduction to our model. So the data of the system are just processed by using a residual neural network architecture. Choosing for its strong, we chose it just because its strong ability to learn complex nonlinear mappings ability while avoiding gradient vanishing problem. And the ResNet model takes the raw data from the hardware system as input and predict the 2D coordinates of the each joints along the CDM. And during the training, the network learns generalized across various bending angles and deformation patterns. And after training, the model can directly reconstruct the manipulator's configuration in real time and eliminating the need of an analytical model and or just the vision tracking during the operations. So we just take a look at our results from the experiment. As we can see from the picture on the middle left, it shows the training process of our model. And this experiment results demonstrate the high accuracy and repeatability of our approach. The trained model achieves a strong coefficient of determinations, and it indicates an excellent correlation between the predicted and ground truth shape. And the picture in the middle, just middle right, just show the predicted and the reconstructed CDM shape connected by dash lines are and we can see the ground truths captured by the cameras are landing nicely around our model outputs. So which shows that the proposed pipeline can efficiently capture the shape variations. So the average of this reconstructed arrow is just about 1.45 millimeter, representing improved 56% improvements in accuracy comparing to our group's previous work approach. We previously developed the capacitive sensor-based methods, and the arrow is just around 2.2 millimeters. So it's a huge improvement. And the results confirms the feasibility of using inexpensive resistive sensors for precise shape sensing of continuum robots in free space and showing us the way toward the real-time integration in the surgical environment and also give us more confidence to miniaturize it for our continuum robot. So in conclusion, we presented a low-cost, precise, data-driven shape sensing system for our continuum manipulators, and it demonstrates the feasibility of resistive sensors for CDM shape sensing and encourage us to take a future step. So for our next step, we're just going to fabricate and miniaturize our own sensor to the real scale CDM and the surgical applications. And thank you for your attendance and attention. And this work is presented at IEEE Sensors 2025.